All right, kids, buckle up. We've got a lot of stuff to learn today. So we're going to talk about this is chapter 3, section 3, I believe, and we're going to get more into the parts of the atom, so atomic structure today. So let's give a little backstory on some things. So we've already learned about elements, right? Are the things on the periodic tables. We have these nice symbols to represent them on the periodic table. And we haven't learned too much about Mendeleev, but we will be talking about him to come. He is the father of the periodic table. The atom, as we know so far, has a nucleus, and it has protons and neutrons inside that nucleus. So, nucleus is made up of protons and neutrons. So we talked about Rutherford discovering the nucleus. Since then, we have discovered there's protons in it and neutrons. And he said that outside the nucleus are these electrons, right? And we mentioned Bohr having that orbital model, and now the wave model of it. So electrons reside outside the nucleus. So what else do we know? An atom is the smallest particle of an element that has the chemical properties of the element. So remember we talked about Democritus and Dalton. They couldn't see an atom. They were coming up with these theories about something that they could not even look at. So again, we've mentioned how science breeds more technology, which gives us more information to learn more things and in science and develop even new technologies. So now we actually have pictures of atoms. So we can use these special kind of microscopes that go down to very, very small scales, electron microscopes. And here are pictures of copper atoms on a silica surface. So let me turn on, where's my little pointer? There it is. So each one of these is a little copper atom. Now, again, atoms are moving really fast, right? They're vibrating, even in a solid, they're vibrating in their space there where they're hanging out. So it's not like you can see electrons and protons in here. So we're still trying to discover more things about them, but at least we can see that they're there. And I could get off on a lot of tangents in this lesson today, but it's going to be long enough. So we're still using new technologies like particle accelerators to see what's in an atom. So what's a particle accelerator? You can click there and go find out more about them, but they're huge. Some of them are, the size of cities. And they're usually underground. And what their basic, goal of some of these is to figure out what's inside the atom. So it would be as if I took my watch and I was like, man, that's a really cool watch. I wonder how it works. And I just smashed it with a hammer. And then I was just looking at all the pieces and trying to say, well, how was that all put together before? Pretty much what they're doing at these particle accelerators. They're colliding these atoms together. They break apart and we see all the tiny little particles and try and imagine how they were there. So you know how Dalton thought the atom was the smallest piece that there could possibly be? And then we thought, okay, protons, neutrons, electrons are the smallest. Now it turns out they're made up of even smaller things. So there's quarks and gluons and bosons and all these things that, again, if you want to learn more about them, you can hit this link right here. But for the purposes of this class, I just need you to know that there are smaller pieces that make them up. That's going to come in handy when we talk about some of the nuclear reactions, nuclear decays. So protons and neutrons are made up of quarks, right? So a quark is a combination of these, and a neutron is a different combination of these, and we'll talk more about those later. Again, 3 quarks could equal a proton or a neutron, depending on the combination that you have. All right. So chemical compounds are made up of atoms. So when we talk about molecules or compounds, they're more than one atom bonded together to create something new and different. So let's go back and rehash Dalton's atomic theory. Remember, we said it was not correct. So he was that early jump forward in chemistry, but Now we've discovered a lot of things were wrong, but that's okay. That's how science works. Um, he was the father of modern chemistry, so it's important to landmark that, but we do know it's wrong. So let's go back and take a look at what he said. He said matter is composed of indivisible particles, right? He got that from Democritus. All atoms of a particular element are identical. So he would say, every single carbon atom is exactly the same. And then different elements have different atoms. So carbon atom is different from an oxygen atom. And then atoms combine in certain whole number ratios to make compounds like water. So two hydrogens and one oxygen gives you water, right? In a chemical reaction, atoms are merely rearranged to form new compounds. They are not created or destroyed. So again, Lavoisier's law of conservation of matter there, and Proust's law of constant composition sort of rolled into one here. So that's all well and good, but what's wrong with it? So first of all, let's talk about the indivisible. Well, obviously that's wrong. We've got nuclear reactions that can divide atoms. We know there's protons, neutrons, electrons, and all these other little particles. All atoms of a particular element are identical. Turns out not. We're about to learn about different isotopes. So there's different types of carbon. So we'll get more into that here in a little bit. And it mainly comes from the difference in the number of neutrons. There's 3 different types of hydrogen. Different elements have different atoms. That one still holds true. Carbon is different from oxygen, right? Atoms combine in certain whole number ratios. Good. Still hanging into that one. That's the law of definite proportions there. So water is always H2O, for example. And then this last one. In a chemical reaction, atoms are merely rearranged to form new compounds. They're not created or destroyed, right? Or changed into atoms of any other elements. Well, yes, except we're going to talk about nuclear reactions. Is going to be the little exception to that rule. That is when an element can change into a different element. Atomic composition. So we've talked about the nucleus has the protons and the neutrons inside, and then the electrons are in this cloud outside of it. Number of electrons is equal to the number of protons. So if you're taking notes, that'd be a good one to write down. In a neutral atom, the electrons are equal to protons. So if I'm using the term atom, it's going to mean it's neutral, and electrons are equal to protons. Electrons are in the space around the nucleus, so electrons are outside the nucleus. And they're extremely small. Atoms are very, very tiny. So if you take 1 teaspoon of water, okay, now imagine the Atlantic Ocean and how many teaspoons of water would be in the Atlantic Ocean. That's a lot of teaspoons. Now triple that, and that's how many atoms are in 1 teaspoon of water. So they're very, very, very small. So here we go. Notes. If you don't have these in your notes, you need to put them in your notes. These are going to be very, very important for the rest of chemistry. So protons. I'm a little lazy. I like to write protons as a P with a plus sign because guess what the charge of a proton is? It's positive. So electrons are positive. They have this mass if you wanted to write it in grams, but let's face it, chemists are lazy. We're not going to do math with that number if we don't have to. Turns out we're going to come up with a new relative mass called an atomic mass unit, and we're going to round the mass of a proton to 1 AMU. So 1 AMU, that's the mass of a proton. Then there's electrons, which I'm going to write with a little E and a negative symbol because guess what the charge of an electron is? It's negative. They have a negative charge, so electrons are negative. They have a relative mass that is very, very, very small. In fact, it would take 2,000 electrons to equal the mass of 1 proton. because they're so tiny, we round them down to 0. We don't even consider them as part of the mass of the atom. Then there's the neutron. Neutrons are neutral, so we write an N with a 0 there to show you that there's a neutral charge on it. No electrical charge. And again, the mass is very, very similar to the mass of a proton, so we also round that to 1 atomic mass unit, or AMU. Okay, one person we haven't talked about yet is Henry Moseley. So, Mendeleev, he puts things in this periodic table, and that's all great, but he has some problems. He has them in order of increasing atomic mass. Well, turns out that there were some issues, and things weren't quite where they should be. And so Henry Moseley comes along and discovers that atoms of each element contain a unique positive charge. And he translates this into the number of protons in the nucleus. So lo and behold, now we have this atomic number, which is going to fix all of Mendeleev's problems with the periodic table. So, since an individual atom is electrically neutral and it has the same number of protons, always equals the number of electrons. So again, if I'm using the term atom, and you can look at your periodic table and figure out the atomic number, then you'll know the number of protons as well as the number of electrons if it's neutral. But atoms can gain and lose electrons, and then they're going to become ions. So again, if I'm using the word atom, it's going to imply that it's neutral and protons equal electrons. If I use the word ion, it's going to imply that it's either gained or lost, and it'll have some charge, so the protons and the electrons will not be the same number. Side note about Henry Moseley. He did all this great work before he was 27. He went off into, I believe it was World War I, was in some battle and in Turkey somewhere and got killed. So by the time World War II rolled around, Britain was like, you know what? We lost this great scientist, so smart, so young. Let's keep the scientists back at home in this war and have them work in the labs. All right, so atomic number is Z. All right, so this is going to seem a little weird. Atomic number, we use Z for it to represent. Now, all atoms of the same element do have the same number of protons in the nucleus, and that's going to be the atomic number Z. So when you look at the periodic table, which you should have one, we've sent home with you. If not, there's always periodic table available pretty easily online, but for here, we put a little block here. So that number at the top, that's the atomic number. That tells you how many protons it has. So this is aluminum. There's its atomic symbol. Aluminum has 13 protons. Now, if I just told you that all atoms have the same number of protons and electrons, and I said, how many protons does aluminum have? You'd go to your periodic table and say, oh, 13. If I said, oh, you have an atom of aluminum, it's neutral, how many electrons does it have? You'd say, it's the same as the protons, 13. Now, the mass down here, the mass of one atom is going to be, remember we said the protons weigh 1, the neutrons weigh 1 AMU, the electrons we don't count. So it would be the protons plus the neutrons. So why is it that we have these weird numbers on the periodic table, like 26.981? These are average atomic masses, and they take into account all the different isotopes of aluminum. So coming up on that here in a minute, what's an isotope of aluminum and how do we get this number? All right, so atomic number was Z. And I know atomic starts with an A, but we represent it Z, whereas mass number is represented by A. Yeah, makes perfect sense, right? So a carbon atom with 6 protons and 6 neutrons is the standard for mass. So when we were looking at mass, we took carbon 12, which is the most common type of carbon. We said, let's say that has a mass, it's got 6 protons, it's got 6 neutrons. Let's divide that up and call those atomic mass units. and say it has 12 AMU. So the mass number of any atom is equal to protons plus neutrons. That should be the number of protons plus the number of neutrons. This is not the same as what you see on the periodic table because the periodic table is an average atomic mass. So, for example, there's different types of boron, but one type of boron has 5 protons and 5 neutrons. So that boron has a mass of 10 atomic mass units. We might call it boron 10. Boom, and we'd write it like this. Oh, I hate that this thing keeps popping up in front of me. I'll sit here and try not to move. So the number at the top that you write at the top, this is a nuclear symbol here. So you write the element's letter symbol, in this case B for boron. You put the mass at the top, that's the 10, and the atomic number goes at the bottom, that's the 5. Okay, so that's one way to write it right here. Over here, I could also write boron and a hyphen and 10, and that tells you I'm talking about boron with a mass of 10. And if I said how many protons does that have, you would look at your periodic table and say, oh, every boron has 5 protons. And then I'd say, well, then how many neutrons does it have? And you'd say, well, the mass is equal to protons plus neutrons, so 10 minus 5 gives me 5. All right, so here's 2 different types of boron. We've got boron 10 and we've got boron 11. The only difference in the two, they're still boron, they still both act like boron, but boron 11 has 1 more neutron in the nucleus. So all borons have the same number of protons. That's what makes them boron. But they can have different numbers of neutrons. So boron 11 has 6 neutrons, while boron 10 only has 5. So again, I can write it like this, boron 10, that means an isotope of boron with a mass of 10 is going to have 5 protons and 5 neutrons because 10 minus 5 gives you 5. But boron 11, which has a mass of 11, can still only have 5 protons. If it's boron, it's going to have 5 protons, which means it must have 6 neutrons because 11 minus 5 gives you 6. So here's 2 types of sodium. There's sodium 23 on the left and sodium 24 on the right. Again, the only difference is the number of neutrons. Both of these are going to do, when you throw them in water, they're going to explode, just like when we put the sodium in water in the lab. When you mix them with chloride, they're going to make sodium chloride salt. But one of them is just a little bit heavier because it has 13 neutrons and a mass of 24, where the other one has 12 neutrons and a mass of 23. Isotopes and their uses. Again, I could go on a tangent here, but I'm trying to make it a little bit short. So you might use them in bone scans with radioactive dyes. There's different types of hydrogen. You might hear somebody talk about heavy water, and in some ways you can tell, where did the water on Earth come from? Did it come from meteors? Was it here through volcanic activity? Those are just some of the things dealing with isotopes. But more, we can talk about that when we're in classroom one day. So, show the name of the element. This is writing atomic symbols. You're going to start by showing the name of the element. Oops, this was moved over for some reason. It should be over here. A hyphen and a mass number. That would be the hyphen notation. And there should be here too. Where'd that go? Show the mass number and the atomic number in the nuclear symbol. So the 23, the mass number goes up here. The 11 should actually be right here. How it got switched over in present mode. So which one of the following represent the isotope of the same element? So if you're looking at all these, and again, it got a little, this 92 should be right over here. It's a little wacky. So if it's the same element, they should all have the same number of what? That's right, protons. So this number at the bottom is the number of protons. So 92 protons, and this one has 93, so they must be different things. If you were to look at your periodic table, you could look it up and say, oh, 92, that's uranium. And so all three of these are uranium. This is not uranium, that's neptunium, right? So it's got 93 protons in its nucleus. So the mass numbers on these are different, but that's just because they have different numbers of neutrons. They're still all uranium. So let's rehash it all one more time. Protons. How do I figure out the number of protons something has? I'll look at the periodic table. So get your periodic table in front of you right now. You're going to need it for the next activities. You can pause and come back when you have it in front of you. Then you have neutrons, also in the nucleus. They have, to figure that out, how do I figure out the number of neutrons? You take the mass number, which you're going to be given if I'm asking you to figure out the number of neutrons. You take the mass number and subtract the number of protons, and then you get the neutrons. What about electrons? Okay, here's where things get a little trickier. If it is an atom, okay, so if I say it is an atom, that means it's neutral and protons equal electrons. So net charge is 0, protons equal electrons. If it is not an atom, if I tell you it's an ion, then it depends on what type of ion it is. So ions have either gained or lost electrons. If they have lost electrons, then they're going to be positive cations. If they gain electrons, they're going to be negative anions because the charge of an electron is negative. So if you have extra negative electrons, you have an overall negative charge. So for each negative charge, add an extra electron. For each positive charge, subtract an electron. Okay? Don't add any protons. That changes the element. So let's see how we do. I'm going to give you some time or you can pause it before I give you the answers to this. So we've got, again, this is carbon 12. The 6 should be right here. Carbon 12. So figure out how many protons it has, how many neutrons, and how many electrons do you think it has for these? And I will go over them. You can pause, figure them out for yourself. Okay. All right, so this carbon 12, if it's carbon, it's going to have 6 protons. So all these are carbon. They should all have 6 protons. Neutrons, you take mass minus protons. So for this one, it would be 6. This one would be 13 minus 6 would be 7. And this one would be 14 minus 6, so it would be 8. And then for electrons, none of these say anything about having a positive or a negative charge. So we assume they're all neutral, and they would all have the same number of electrons and protons, so all of those would be 6. Oop, there's your answer. All right. An atom has 14 protons and 20 neutrons. Its atomic number is what? Hopefully you said 14. So we could look at our periodic table and be like, oh, that must be silicon, right? Because it has 14 protons, has atomic number of 14. Its mass number would be what? That's right, 34, because to find the mass, you take protons plus neutrons. The element is, oh, I already gave that away, silicon. That's right, 14 protons. And another isotope would be which one of those? It would have to have 14 protons, so it'd either be 2 or 3, right? Both of those having 14 protons. So it could either be 2 or 3, even though that one should be over here. Silly thing. Let's talk about ions. Ions are atoms or groups of atoms that have a positive or a negative charge. So they can be positive or negative. They have become positive or negative by either gaining or losing electrons. So taking away an electron from an atom gives you a cation with a positive charge. So cations are positive. Adding an electron gives you an anion. Those are negative anions. So to tell the difference between an atom and an ion, you should see little charges written to them in superscripts. So here's some examples. A sodium with a plus sign like that. That means that sodium has a +1 charge. So it's a cation, which means it has lost an electron. So look at your periodic table right now. Find sodium. When you find sodium, you see its atomic number is 11. If that little plus was not here, if this plus wasn't there, then I would say, oh, it has 11 protons and 11 electrons. But since that plus is there, I'll say, well, it has 11 protons, and it would have had 11 electrons, but it has lost one because it's positive. So it now only has 10 electrons. To help you remember, there's a little joke for you. So, cation walks into a bar. Bartender says, what's the matter? He says, well, I think I lost an electron. Bartender says, are you sure? The cation says, yeah, I'm positive. There you go. So, cations have lost their electrons. They're positive. Calcium here also has a +2 charge written next to it. So, if you look at calcium on your periodic table, it has atomic number of 20. It would have 20 electrons, except with that +2, we know it has lost 2, so it only has 18. That iodine, if you look at your periodic table, has 53 protons. It would have 53 electrons, but the negative sign next to it means it has gained an extra one, so it has 54. That oxygen with the -2, well, it had 8 protons and it would have had 8 electrons, but it's gained 2 electrons, so it has 10. All right. Hopefully we've got that in your heads now. So, forming cations, how does it happen? So here's an example with magnesium cation and an anion. So the cation forms when an atom loses one or more electrons. So you take your magnesium, which had 12 protons and electrons, and then it lost 2, so now it's a magnesium with a +2. An anion happens when you gain one or more electrons. So you had your fluorine atom, and you gained an electron. Now it's fluoride, it's an ion. Predicting ionic charges. In general, metals are going to lose electrons and become cations. We'll talk more about why later. Nonmetals tend to like to gain electrons and become anions. All right, here we go. Pause this, see if you can figure these out, and then we'll go over it together. All right, coming back from your pause, we have potassium. Your number of protons is 19, right? To find the neutrons, I want mass minus protons. So 39 minus 19 would give me 20. Now, to find the electrons, it had 19 protons, so it would have had 19, but this plus means it's lost. Are you sure? Yeah, it's positive. So they've lost 1, so it's 18. Over here, 8 is the protons. 16 minus 8 gives me 8 for the neutrons. It would have had 8 protons and 8 electrons, except it gained 2, so now it has 10 electrons. Over here, calcium has 20 protons, 21 neutrons. It would have had 20 protons if it hadn't lost 2, So it has 18 18 electrons. Did I say neutrons? All right, now for this one, you want to write the nuclear symbol. So you're trying to make these look like this. Now you need to figure out the symbol, the atomic number, the mass number, and the charge. So go ahead and give it a shot. And then we will add them on there and I'll tell you. So over here, you've got 8 protons. So I'm going to look at my periodic table and say, what has 8 protons? Oh, that must be oxygen. I'd write O right here. Then I would say, what is the number? So I'd put an 8 down here for the number of protons. And to figure out the mass, I'd add the protons and neutrons together. So there'd be a 16 here. And 8 electrons, since it's the same as the protons, means I don't need to give it a charge. So, oops, thought I might have an answer on there, but I didn't. Over here, we've got 17 protons, 20 neutrons, 17 electrons. So already I can be like, oh, no charge on this one. So I'm going to write my 17 down at the bottom like a subscript. Look up what's number 17. Oh, that's chlorine. So I'd write chlorine here. And then I'd put my mass at the top. So protons plus neutrons. So 37 up at the superscript. Down the next one, I've got 47 protons, but 46 electrons, which means I have one extra positive. So it's going to have a +1 charge, whatever it is. If it has 47 protons, then that must be silver. So Ag for my symbol. 47 down here, and then my mass will be 47 plus 60, so 107 up here. All right, on your periodic tables, like we said, metals tend to lose electrons, nonmetals tend to gain. So everything in this column is generally going to lose 1 electron and make a +1 ion. Everything in this column is going to want to lose 2 electrons and make a +2. We'll talk about why later. Everything over here, this last column, they don't do anything. These are the noble gases. They're holding all their electrons. Nobody's taking any there, or gaining any. Over here, this row, they really want 1 electron, so they're going to steal and become -1 ions. These guys want 2 electrons. They're going to gain 2 and become -2. These guys right here tend to want 3. They'll be -3s. So you might want to write those at the top of your periodic table. Oh, by the way, the whole reason they do that, they all want to be like noble gases. Again, more on why later. Now, an average atomic mass. This is that one on the periodic table. Why isn't it a whole number if it's just protons plus neutrons? Because there are different isotopes, and we have to reflect that in our mass on the periodic table. So, because there's 2 different types of boron, there's boron 10 and boron 11. What are we going to put on the periodic table? So, if you get just an average sample of boron, 80% of it is going to be boron 11. So most of it's boron 11. But 20% is going to be boron 10. So we can't just put 10 or 11 as the mass on the periodic table. We have to represent the fact that 80% of the sample is going to be boron 11 and 20% is going to be boron 10. So we do that by getting an average atomic weight. So we take the percentage, and we've just turned the percentage into 0.2. So 20 becomes 0.2. How do I do that? Just divide by 100. Multiply that by the mass. So 20% times 10. You do that for every isotope. So here's 80% times 11. If there were more isotopes, we would add those onto it. And then you add them all together, and I get 10.8 AMUs. So your average sample of boron is going to have an average mass of 10.8 AMUs. So that's going to help us figure out how many atoms we're putting into something. All right, because of the existence of isotopes, a collection of atoms has an average value. So again, here's two types of lithium. Lithium 6, lithium 7. To figure out the average atomic mass, we're going to take the percentage, turn it into a decimal, so move it over twice, divided by 100. So 0.075 times 6, 0.925 times 7, and then add those together, and you would get your mass of lithium. So go ahead and try these on your own, and you can pause the video, try it. You'll know you're right if your answer agrees with what you see on the periodic table. All right, so more on the periodic table later, but basically this little dividing line here is sort of your divider between metals and non-metals. And the ones that are right on the line tend to be your semi-metals. So we'll talk more about that in an upcoming unit. I think that's enough for one day. You guys have a good day. And now you can go answer some questions.